now we're going to talk about pipe flow and uses of viscosity. Figure I'd make it 2 different videos because there was no new information in the last video. It's just a recap of old stuff. I'll put it up on YouTube if anybody wants to see it, but this is where the new stuff is. So let's see. Today we're going to talk about, and how long do I have? 20 minutes. Okay, great. We'll talk about pipe flow and the Reynolds number. Let's talk about the Reynolds number first because it's pretty fast. I think that's a concept that people mostly get, but there's a lot of deep beauty in the idea of the Reynolds number. So we write down Navier Stokes, dV dt plus v dot grad v equals -1 over rho grad p plus a new del squared v. So nu is how coupled together different streams of velocity are. So if I have a stream of velocity that's going this way, nu tells me how tightly coupled is the stream that's immediately next to it. Bigger nu, more coupling. That way I remember what I'm supposed to be talking about. Okay, so this is the thing that you're interested in. This is how the velocity is changing. This is one of the ways that the velocity is changing. The velocity is changing by the velocity bringing in different velocity. I like that sentence, right? The velocity is carrying velocity, and that's why you have velocity. That's what this says. How awful is that? This bit, v dot grad, is what's pushing velocity. V dot grad v is pushing velocity. If I had, say, if I wanted to think about a scalar concentration density, so say I dump a bunch of pollutant into the room somehow. And I have a room and I have some pollutant, let's call it C. dC dt plus v dot grad C is going to be 0 because there's no source term for C. You can't make any more C. So v dot grad, and you get this from the same way you got it before. The v dot grad is pushing this. So if I have a bump in concentration and I've got some velocity, let's say I don't have a bump in concentration. Let's say I just have, so here is 0. Here is concentration of stuff at some level. I have a velocity in this direction, and I'm sitting here. Say this is a river, and I've got garbage in the river. Say I've got a uniform constant level of garbage in the river, and I'm sitting here. I don't see any change in the constant in the garbage that I see. But if I have, say, a bump of garbage, then grad C is not 0. So v dot grad C is going to push this bump of garbage past me, and I will experience that bump of garbage, or whatever. So v dot grad is pushing by velocity. So v dot grad v is pushing the velocity with the velocity. The velocity carries itself, and it is a quantity that you care about. So this is stuff moving around. We call this the kinematic term. It's the body motion. It's the motion of the fluids. Sometimes that's the most important thing. Pressure is whatever you're doing. This is an outside knob. So this is Jesus lets me turn the pressure however I want. So it's not really very interesting. This is really where my boundary conditions come from. What the flow does, the other part of the flow, is the v dot del squared v, because we're looking at what the velocity is doing. What does this do? We haven't talked too much about del squared yet, but I will. It's diffusion. It spreads stuff out. That's what that operator does. So if I have a spike, and that's the only operator I have, it spreads things out. So this is called the diffusive term. So for instance, if I have a pool and I shoot a very small jet of water into the pool, then that will then train the water around it to accelerate, which will train the water around it to accelerate. So what starts off as a thin little jet starts to become kind of a wider stream of velocity. So I've got this one tiny jet, and it spreads out as it entrains everything else. That jet spreads out and smears out. So this term smears things out. Yeah.
So in the jet example that you have,
yeah,
when it's shooting out is as a higher coupling, would the diffusion be greater?
Yeah, if you had more viscosity, you would have a wider stream and it'd spread out more. We gotta assume that there's like no end to this pool so that we don't have pressure terms, because weird things will happen. So we have these two terms, and we'll talk about this balance between pushing stuff around and diffusing things a lot. So I have these two terms. Now, let's for a minute ignore the last term. So I just have dV dt plus v dot grad v equals minus 1 over rho grad p. Let's change units. I'm going to say, let's look at what the units are doing. This is in meters per second per second. What are the units on this one? Pro tip, you don't have to think very hard because it better as hell have the same units as the first term. This is in, okay, so I've got two velocities. That's a meter squared. I got a meters squared per second squared per meter. Okay, so this is in meters per second squared. This one is also in meters per second squared. And this one, harder to see. What's the units on pressure?
Force per area.
Force per area. That is not the unit. Those are not actually the useful units to deal with pressure, it turns out, unless you have like an actual area, like if you have an object that you're dealing with.
Well,
the more useful is energy per volume, which gives you the same answer because force times distance is energy, right? So they're only different by a dx. Area and volume are also only different by a dx. So the units on pressure are ergs per centimeter cubed. I've talked to you about what an erg is. You guys know what an erg is. Okay, there's a long, I will go on the long tirade about why CGS is vastly superior to MKS, and MKS is a dumb unit system, and CGS is a sensible unit system. We'll go on that tirade in a minute. The erg is the CGS unit for energy. Let's talk about CGS units for a second. Just real fast. Oh, and then I gotta make sure I don't run out of time to talk about all the stuff I care about. So, kind of a pointless aside, but I do everything in CGS because I'm an astronomer. And astrophysicists back in the 50s did not adopt MKS for reasons that I'll ramble along. MKS invokes a whole other unit and a whole other physical constant that you have to measure and define, and it doesn't make any sense. You don't need that other unit. You don't need to introduce a new current. More importantly, electric fields and magnetic fields ought to have the same units, and they don't in MKS. They do in CGS. CGS is superior. So you have grams, centimeters, and seconds, which are similar to the kilograms, meters, and also seconds that you're used to dealing with in your other science classes. But then, what are the derived quantities? You have joules, and you have ergs. What's a joule? What's that for meter? Oh, dope. Was that, so what was it?
kilogram meter squared per second squared.
This is a kilogram meters squared per second squared, so what's an erg?
Gram centimeters squared per second squared.
Yeah, gram centimeters squared per second squared. And what's a dyne? Dyne is equivalent to a Newton. And what's that?
Kilogram meter per second squared.
Yeah, this is a kilogram meter per second squared. That's force times acceleration, and this is the same thing. Centimeter, gram centimeter per second squared. one of the reasons that astronomers use CGS is that the mass of the sun in CGS is a really stupid large number. It's like 10 to the 36. The mass of the sun in MKS, also a stupid big number, is like 10 to the 35. It's a really dumb number. So using these tiny little numbers doesn't really affect anything because there's a lot of them. So how big is an erg, like energy-wise? How much energy is there? Well, it's a gram. How much is a gram? Like $20, but like it's like a paperclip, right? How much is a centimeter per second? I get a lot of mileage out of that one. How much is a centimeter per second? It's not very fast, right? So an erg is like an ant doing a push-up. Not very much energy at all. A joule, a kilogram's pretty heavy, and a meter per second is pretty quick, so a joule will mess you up. But an erg is not a very big amount of energy. And yet we still measure supernova energy, which are the biggest explosions in the world, in ergs, because there's 10 to the 50 of them. It's a stupid large number anyway. Okay, so that's a running thing. I'm always going to use CGS just because it's what I'm more comfortable with. Okay, so back to units. Units on this. What are the units on this? So this is energy per volume, per length, per density. You wind up, you get the same thing, meters per second squared. So this is an energy per volume, and then you got another length, but then you've got another per volume. So you got grams here, that cancels the grams here. You work out the algebra, you get the same answer. Okay. Now, let's change unit systems. Let's use this stupid British one, stone. Oh no, stone is mass.
Yeah.
Let's make up a new unit. I'm going to call it the stone anyway. Because this exercise, it doesn't matter. The units in this equation don't matter because I've got all of these things. If I change the units, they all change the same, right? Because I'm just changing this. I'm just changing the scale of what I call the things in this equation. So I can change the units of Euler. I can change the units all day. I can rescale Euler all day. Navier-Stokes, however, you get the same units, but this is a physical quantity, and it cares what units you're talking about. Pressure, like all the rest of them, I can rescale the units and it doesn't matter, but this is a physical quantity that cares about the protons and the electrons and how they're interacting with each other. So I can no longer just rescale all willy-nilly when I have this term here. So let's look at the sizes of how big each one of these things are. So when I do rescale the units or I rescale the equations, well, how do I do it? So here I've got a velocity, and a length. This is the thing that I'm looking at, so that's the question that I have. So that's not, I'm going to ignore that. This is a boundary condition, I'm going to ignore that too. Because I can rescale pressure and stuff just fine. But nu, how do I rescale it and still keep nu in check? So this is nu times v divided by 2 length squared. 2 lengths. So the order of magnitude of this thing, so I can't really, so the units are part of it, but really you need to know how big are the various flows relative to each other. How big is the velocity relative to the viscosity? If I don't have this term here, then I can change my units and the pressure will just adjust. It'll just sort it out. But the viscosity doesn't because it's molecules. So let's look at the ratio of this guy to this guy. So this is the kinematic term. So I've got VV over L divided by nu V over L squared. I do that algebra and I'm left with velocity times length divided by nu. And so what I did is that gives me the ratio of this term to this term.
It's the Reynolds number, is it not?
This is the Reynolds number. So I'm looking at what the hard term is, so this term is complicated and makes things messy. The nonlinear term, this is where the chaos comes from. I'll show you that later. But this is where the messiness comes from, and this is where the niceness comes from. So you compare the messiness to the niceness, and you get the Reynolds number. So it is the scale that you rescale things with. So I can rewrite the Navier-Stokes equation in a way that I can use whatever units I want if I instead write it like dv dt plus v dot grad v plus 1 over rho equals minus 1 over rho grad p plus 1 over the Reynolds number del squared v. If I write it like this, all I've really done is replace nu with 1 over the Reynolds number. Then I have a scale-free equation as long as I keep the Reynolds number constant. As long as the Reynolds number is the same, then I have a scale-free equation. So what does it do? It tells me how much this term I have. This term is the chaos term, and this term is the smooth term. So the bigger the Reynolds number is, the bigger this chaos term is, the bigger the nonlinear term is, and the bigger the mess is. So how big is the Reynolds number? So a Reynolds number of like 1,000 is getting to be pretty turbulent. So when you're feeling turbulence in the air in an airplane, that's high Reynolds number flow. It's of a few thousand. Bigger than that is more turbulent. A couple hundred is still kind of turbulent. And here, I'm running out of time. I will bring in some. I forgot to bring in. There's a really great graphic in the. Oh, is it in the book? Maybe it's in the book. And maybe you guys have seen it. Let me see. I've read too many fluid dynamics books, and I can't remember which pictures. Oh yeah, this one is seen. So this picture here shows you what increasing the Reynolds number looks like, and hopefully you all took a look at this. So at a small Reynolds number, you have a really smooth flow. At a Reynolds number of like 100, you start to get flow that is random and not smooth anymore, but is not yet turbulent. And then when you get up to about 1,000, then you have fully developed turbulence, and the flow is totally chaotic. And we'll talk about what I mean by that later. Let's see. That's what I'm going to say for today. I'll do soy flow on Tuesday because I didn't get to it today, and other stuff. New homework up tonight, due next Thursday. Reading due Monday. I think that's everything you guys need to know from me. Do you guys have any questions? Everybody good? All right. Thanks very much. Have a good rest of the day.